Let's welcome Professor Michel Waldschmidt. And as all of us know that, he's a constant traveler and he goes, even in India, he goes to very remote places. So we are very lucky that today all the speakers are, not only established mathematicians, but they have blessings on Indian number theory scene. They have really given a direction for ages, and I hope they will keep doing this for times to come. Thank you very much. You may begin your talk.
Thank you very much.
Circulant determinants and Clifford algebras.
Yes, so thank you, Srini. I wish to thank the organizers for inviting me. And I would like to start with some reminiscences of my many visits to India. That would take half an hour, but I will make it brief. My first visit was in 1976 when I was invited by Professor Ramachandra in Tata Institute in Bombay. And I came to Chennai at that time for just 1 weekend, but I did not visit some institute. It was for tourism and for going to Pondicherry. My next visit was probably in 1984. And when I went, I met several mathematicians. I went to the Mathematical Institute, but I went to see Krishna, and I was invited by his father to his home, Kamran Nivas, and I have a very fond memory of this first visit of me to this place. I came back in 1985, just before going to Institute of Princeton in IIAS, and then I went again, well, a couple of times, but the most important visit of me here was in 1988 when I came with my family, my wife, my son, and my daughter. My son was 12 and my daughter was 10. And we were invited in Kamran Nivas, and we have a very fond memory of this visit and the magnificent buffet breakfast that we had at that time. That was really something. I went also in 1996. I organized a conference in Trichy with Kumar Murthy, and the proceedings have been published. And at this conference, two other specialists of Diophantine approximation, Dale Brunawell and Wolfgang Schmidt, participated, and then they came here. And 3 days in a row, we gave a talk in Kamran Nivas, Brunawell first, and then me, and then Wolfgang Schmidt. So that was a very great event. And I came many of the times. The last time I came, I did not give a talk, but I was invited with some students who gave me a lecture on what they were taught by Aladi Ramakrishnan. So I have some very fond memories of my visit, and I chose two topics. One is circulant determinant, and the other is Clifford algebra. So there is no direct connection between the two topics. The connection is just that the circulant determinant is a problem which was raised by Aladi Ramakrishnan, and I will explain you the solution. It's some elementary calculus. And the second part, it's just to explain an example where the Clifford algebras, which is something which is very much used in physics, occurs also in transcendental number theory. So I will start with a paper by Aladi Ramakrishnan, Pythagoras to Lorentz via Fermat, spanning the interval with light and daylight. So it was in 2003. He started with the Pythagorean equation, which he wrote a square minus b square equals c square. And he noticed that the left-hand side is the determinant of ABBA, which is a square minus b square. And then he suggested to look at a three-dimensional analog of, instead of a 2 by 2 matrix, we take a 3 by 3 matrix, and we take the so-called circulant matrix. So if you look at this circulant matrix, we use a shift, and the shift is from right to left. Very often we use the shift in the other way, but I take the same notation as he takes, and this is why there is a minus sign here. So we will not be so much interested with the signs, so very often we will write plus or minus without taking care of the sign. Aladi Ramakrishnan was interested in the absolute value of the determinant. And thanks to that, he suggested a cubic analog of the Lorentz transformation. And this cubic analog is the one which is written here. A sum of 3 cubes minus 3 times the product is a cube. And he suggested also a generalization to n by n circulant determinant. And this is where he asked the question. So I wrote a letter to him in 2000 when I said that this was published in 2003. His paper was before that, but it was published 3 years after my answer, and with this publication is my answer. So I told him, I am glad to tell you that the conjectures that you stated are true, and the conjecture were about a circulant determinant. It's a k by k determinant. The first row is z1, zk, and then you shift, as I said, to the left. And so then you have zk, z1, zk minus 1, and so on, up to z2, z3, zk, and z1. So we have a determinant. We look at the polynomial, which is the determinant of this circulant determinant. And pk of z is a polynomial in one variable, where you replace z2, zk minus 1 by z minus 1, z minus k plus 1. So this is a polynomial that he was interested in, and he asked whether it is true that it is a constant times z minus k minus 1 over 2. And this is what I wish to explain the proof, which is just some computation. And he asked, he was interested in this, especially when k is even. And when k is odd, excuse me. When k is odd, then the value at m plus n is just a multiple of n times a constant. And I will explain that the constant is 2m plus 1 to the power 2n. And then he had another conjecture in the case which is even, and this conjecture is the following. You take the circulant determinant of order 2m, and you start with n plus m, you go up to n minus m, but you omit the n which is in the middle. So it's this circulant determinant, and this conjecture was that this is a constant times n, this n which is here, for all n. And C of m depends only on m. So I will give a short proof, some proof of this result, which is not too difficult. But I first give some examples. For P2, it is the determinant of z, z minus 1, z minus 1, z. So you just compute it. You find 2z minus 1, which fits the result which I mentioned. For P3, which is C3 of z, z minus 1, z minus 2, so this is this determinant. And when you expand it, you have this formula, which is a polynomial of degree 3, but the terms of degree 2 and 3 disappear, and then you find minus 9 times z minus 1. So this was for the case which was even. Now for the case which is odd, the circulant determinant, you omit the n, which is in the middle here. So you have C2 of n plus 1 and n minus 1. Again, you compute it, and you find that it is 4n for the index 2. And for the index 4, because we take even numbers, so you omit the n here, you have 4 numbers. You write this expression, and you expand, and you find that it is minus 144 times n. And I give another example, which is for n equal 3. So the value, the determinant is a 6 by 6 the determinant of a matrix. And you find the multiple of n, and this multiple is 2 to the 11 times 3 square. I must say I do not have a close formula like this for the general value of 2k. It may not be too difficult, but I do not have it. But the question was just to know that it is a multiple of n. Okay, so these are the examples, and now let us go to the proof. The first remark, which is that if you start with the matrix A, which is with constant coefficients, and if you look at the matrix where you replace each aij by z plus aij, you have a polynomial in z, but the polynomial is just a polynomial of degree 1. And this is not difficult to see. And so the constant coefficient will be the determinant of A, because it's when z equals 0. And then you have Cz plus determinant of A. Why is it so? It is just that you replace each row by the first row by the first one with the difference with the first one. You replace each row but the first one by the difference with the first one. So all the rows will not involve Z, and so you just have the first row which has Z, and then you have nothing more. So this will give more or less the answer for the first formula. For the second one, you notice that if k is equal to 2m, when you look at this determinant here, where you do not have 0, but you take n equals 0, it's easy to see that the sum of all rows, and as well as the sum of all columns, is 0, and the determinant is 0. This is why there is no coefficient, the determinant of A. And so when we use these two simple facts, we deduce that the determinant in the even case is a constant times n, and in the general case, pk of z is ck z minus k minus 1 over 2. So this answers the question, but we would like to give another proof in such a way that we can give a closed formula for ck. And for that, we use a result which is well known and which is not difficult to prove on the circulant determinant. If we multiply the columns by 1 zeta to the k minus 1, where zeta is the root of unity of order k, then we see that this determinant is divisible by this linear form. You look at the coefficient of maximum coefficient of z1 and you deduce that the constant is 1. So ck of z1, zk is this product of k values. Zeta takes k values. So we can write it like this. The product for zeta, which ranges over the kth root of unity, times this sum, which is here. So we have to look at the sum which is here in the special case which we are interested in, which is with z minus I. So pk of z is this product of these forms with z. And now when we compute the sum of the zeta I, it's well known by looking at the minimal polynomial of zeta, that it is k for zeta equal 1 and 0 for zeta different from 1. And from that we deduce not only the previous formula, but we deduce also the value of ck, which is a closed formula with k which corresponds to zeta equal 1, and then the other one do not involve the z which was here. And then we have to compute the sum of I, zeta to the I, and so this is the sum that we have to compute. And to compute it, we notice that it is the value of the derivative of the polynomial z to the k minus 1 divided by z minus 1, so this polynomial here. If you take the derivative, you obtain essentially that you have to multiply by zeta. And so when you look at this derivative, this is k zk minus 1 over z minus 1 minus zk minus 1 over z minus 1 squared, just the derivative of this. But if z is replaced by a kth root of unity, this is 0. And so you have zeta f prime of zeta equal k over zeta minus 1. And you have now to compute the product of zeta minus 1. And this is nothing else than the resultant of z minus 1 and f of z. F was the polynomial 1 plus z to the k minus 1. And so this resultant is minus 1 to the k minus 1 f of 1, and f of 1 is k. And therefore, we find this formula here with k to the power k minus 2 for zeta different from 1. And for zeta equal 1, we have the coefficient k. So we get k to the k minus 1. So this completes the proof. I would like to give another reference on this topic, which is a paper that I wrote with Shigeru Kanemitsu on matrices of finite abelian groups, finite Fourier transform and codes. And it was mentioned yesterday in the lecture by Yaganathan that there is a connection between matrices of abelian group and finite Fourier transform. But there is another connection with codes, which is quoted in this paper with Shigeru. Okay, so this was the first part of my talk. And for the second part, it is related with Clifford algebra. I start with very basic things concerning transcendental numbers, since they are there may be some physicists in the audience. So I would like to recall what is an algebraic number. An algebraic number is a complex number which is a root of a polynomial with rational coefficients. And if a number is not algebraic, then we say that it is transcendental. So we have example of algebraic numbers, which are the rational numbers, square root of 2, the roots of unity, which are algebraic. And we have example of transcendental numbers, e, pi, and almost all numbers for Lebesgue's measure. We have a good collection of transcendental numbers, but we have much more conjectures than theorems, and I will come back to this fact right now. There is a generalization of the notion of algebraic and transcendental numbers, which goes in the direction of the lecture of Ram, which is to involve several variables. And indeed, instead of taking one variable p, we take n variables, x1, xn, and we have complex numbers, alpha 1, alpha n. We say that they are algebraically dependent if there exists a non-zero polynomial such that p of alpha 1, alpha n is 0, and otherwise we say that they are algebraically independent. This is much more general, because if you have algebraically independent numbers, then each of them is transcendental. Because if you take just a polynomial in one variable, it will not vanish at each of these points. So it's more general than the transcendental. Among the results which are known on transcendental numbers, there is the fact that E is transcendental, which was proved by Hermite in 1873, and the fact that pi is transcendental, which was proved by Lindemann in 1982. Now there is a remark which is that if you have two numbers a and b, if a plus b and ab are algebraic, then a and b, both of them are algebraic. This is just because they are roots of the equation x squared minus sx plus p. S is the sum and p is the product. So if both numbers are algebraic, then a and b are algebraic. And as a consequence, if you look at the two numbers e plus pi and e pi, each of them is transcendental. In fact, it's sufficient that one of them is transcendental to deduce that among the two numbers, at least one is transcendental. So this is the kind of result that we have to deal with in transcendental number theory, because we do not have many results. And so sometimes we have partial results. We conjecture that both numbers, e plus pi and e pi, are transcendental, both of them, but we do not know. And the main, a stronger conjecture would be that e and pi are algebraically independent, which means that they satisfy no algebraic relation, but we do not know. So very often we have this kind of result. One of the two statements is correct. I will give another example, which is a work which I did in 1972, and Dave Ronawell, that I mentioned before when he came to Cameron-Nivas, he published it exactly at the same time in the same journal and independently. And the result is the following. Either e and pi are algebraically, one at least of the two statements is true, e and pi are algebraically independent, and exponential pi square is a transcendental number. We do not know to prove that exponential pi square is transcendental, and so we just have a partial result. One of the two statements is true, and the conjecture is that e pi exponential pi square are algebraically independent. I gave this example just to explain why we have some partial result on algebraic independence. The main conjecture, which would have a lot of consequences in number theory, is that if you take logarithm of algebraic numbers which do not satisfy linear dependence relations, then they do not satisfy algebraic independent condition. And this is the main conjecture. But we know very few things. We do not know that there are two algebraically independent logarithms of algebraic numbers. This is not known. That the transcendental degree is at least 2, we do not know. And we do not know something about non-trivial quadratic relations. So this is the kind of problem on which people in transcendental number theory are working. And with Damien Roy, we have a partial result, which is that one at least of the two problems which I mentioned has a positive answer. We take logarithm of algebraic numbers which are linearly independent, at least one of the two following statements is true. The first statement is at least two of the numbers log alpha 1, log alpha n are algebraically independent. And the second is that if you take a non-zero homogeneous polynomial of degree 2, the quadratic form, then this polynomial does not vanish at log alpha 1, log alpha n. So this is the result for which we use Clifford algebra. And so I just mentioned that Clifford was an English mathematician who studied non-Euclidean geometry. And he introduced what is called Clifford algebra, which is a generalization of Grassmann exterior algebra. So I will use, with this work with Damien Roy, we use Clifford algebra. I first recall the definition of a Clifford algebra associated to a quadratic form with complex coefficients. So we have a map Q, which is a quadratic form. The Clifford algebra attached to Q is a simple algebra of dimension 2 to the m. Here is the m of C. It contains Cm as a vector subspace. It is spanned by Cm as a C algebra, and the square of an element in Cm is given by Q of V, where Q is the given quadratic form, for all V in Cm. This may not be immediately obvious that it is the same definition as is used in physics, but it is the same Clifford algebra. So if we have a basis of Cm over C, to have a basis of this algebra A over C, we just take the product VI1, VIR, where I1 is less than I2, less than IR, so you have the right number of elements 2 to the m. So this is the Clifford algebra over C. We need it over Q. And so for that, we take a quadratic form which has coefficients in Q. And we take the sub-Q algebra of A, which is spanned by Q to the m into C to the m. And Q0 is the restriction of Q to Q to the m. And A0, which is this algebra, the sub-Q algebra, is the Clifford algebra attached to Q0. It has dimension 2 to the m over Q. Now, this is the difference, it's Q over Q instead of C. And any basis of A0 over Q is the basis of A over Q. So we fix such a basis. For each V in Cm, so now it's in Cm, not only in Qm. For each V in Cm, we look at the matrix of the linear map, which is the multiplication by V. Because V square is Q of V times 1, we have the square of this matrix, which is Q of V times the identity, the diagonal matrix. And therefore, the determinant of MV is Q of V to the power 2 to the m divided by 2, so 2 to the m minus 1. If Q of V is different from 0, then MV is a regular matrix. But the main point is that if Q of V is equal to 0, then MV has a rank which is less than 2 to the m minus 1. This is the property of Clifford algebra that we use. In principle, we can say that the rank is less than 2 to the m strictly, but it is less than 2 to the m minus 1. And so we have a map from Cm to the set of matrices, which maps an element V to this matrix MV, which is a multiplication by V. And so the Clifford algebra is used in the following way. If you have a non-zero quadratic form, if we look at the set of zeros of Q in C to the m, then there is an injective linear map, which I just defined before, from Cm to the matrices, such that for all V in Cm, the rank of the image is a multiple of 2 to the m minus 1. And the set of zeros of Q is a set of V, so that the determinant of theta of V is 0. And so this is in this paper, and this is what we use for the proof of the transcendence result. So with this, I thank you, and I conclude.
Questions, please?
Yes, Ram.
Thank you for this nice overview. Your statement that E pi and E the pi squared, does that follow? Would that follow from Shanuel conjecture?
Yes.
Oh, okay.
Yes.
So that's kind of okay. So I was just wondering.
Yes.
Because I know that E and pi being algebraically going to follow from Shanuel, but pi squared.
Yes, it's an exercise. You take numbers which are constructed, built with the log width, with exponential, with pi, and if you do not put them in a too obvious way, the conjecture of Chanuel will imply that they are algebraically independent.
All three.
We have to use the conjecture of Chanuel, not the conjecture of algebraic independence of log width, which I mentioned, which is another special case of Chanuel. Yes.
Sorry.
Yeah, I was wondering about your result that you mentioned that either E and pi are algebraically independent or e to the pi square is transcendental. So I wanted to ask, can you give a brief introduction on how you would even start thinking that these two statements would be related to each other or connected to each other in some way? Like, why would you even think that these two statements are related? How would you even start thinking about this?
Yes. Okay. So the fact is that this is part of theorem that we proved at the same time and with the same proof, Dave Brunauel and myself, which is related with one of the problems of Schneider, which is the 8th problem of Schneider. So Schneider asked, is it proof that one of the two numbers, exponential of E and exponential of E squared, is transcendental? And we proved this result, but this result is a special case of a more general result where you have x1, x2, y1, y2, and we look at the exponential of xi, yj. So we worked out the general result, and again, it's exactly the same that we did, Dave Brunauel and myself. And then, when we had this result, we looked at the consequences, and we found this consequence. And we are not so far of proving that among the numbers pi, e, and exponential pi square, two of them are algebraically independent, but we did not succeed to get that. But so we did not start by saying we will prove this result, that one is true. We got a general statement, and from this statement we deduce some corollaries.
Yeah. Anyone else? All right, already Krishna Swami. Krishna.
So I just have a comment here, and I stood up because I wanted to say something about Michel himself. So he referred to when he first came to Madras and we met. I will also say something about when I first heard of you in a very significant way, and that's related to what you put on the slide and related to what Ramurthy asked. So there was a conference, Summer Institute in Ann Arbor in 1973, and I was one of two undergraduate participants in that Summer Institute. It was very gracious of Montgomery and Lewis to admit me as undergraduate participants, and in those days, there was no specific culture or grants given which said that if you want to have a conference, you should have money for graduate students and undergraduate students. It was nothing like that. So anyway, I attended this conference, and one of the lectures I remember was of Dale Brownowell. And in that lecture, Brownowell was talking a lot about his work and the work of Waldschmidt. And this particular theorem, which was proved in 1972, and of course this was Summer Institute in 1973. So that's when I heard of Michel Waldschmidt. The connection with Ramurthy's comment is, I think Brownowell is a student of Chanuel.
Oh, that is true, yes.
Okay. Thank you, Krishna. So let us thank Michel once again for the wonderful talk. Thank you very much. I request Shauli to kindly come and present.